Hi everybody, this is our last unit on intermolecular forces. This is pretty short. This lesson is long because this goes over the different types of intermolecular forces in a lot of detail and the phases of matter. The other three are quite short. I have everything posted in OneNote for you in terms of things you need to complete, a nice schedule. So please let me know if you have any questions as we go along. So this first lesson is on states of matter and intermolecular forces. So the beginning part here is just really a review. So the difference between states of matter is the distance between the particles. And you've seen so many particle diagrams at this point. You're pretty familiar with how to draw them or how to, identify a particular solid. So in terms of your entropy, it would be decreasing as you get the particles closer together and more organized. Free range of motion for gases. They're moving around, but they're still touching for a liquid, and they have that ordered arrangement for solids. They're in fixed positions. We refer to both liquids and solids as condensed phases or condensed states because those particles are touching one another. It's really not something that you're tested on, but, whatever. Nice diagram. So there's a couple different things that will determine the phase of matter that a particular substance is in at a particular temperature and pressure. It has to do with the kinetic energy of the particles, which is them moving around, versus, right, they're antagonistic, right, versus the strength of the attractions between the particles. This chart I have just isolated on a separate page in OneNote. I think it says phases of matter chart or something like that. But this is really great for just characteristics of states of matter. I'm not going to read this to you. This is pretty much, Regents level basic material. Volume and shape of the container for a gas, compressible. We did a whole unit on gases at the beginning of the year. Remember that? Oh my gosh. What you need to remember for phase changes is when a substance changes phase, the molecules remain intact. The only thing you're changing are the forces between the molecules, not those within the molecules, right? So you're not breaking chemical bonds. You're not breaking a covalent bond or an ionic bond or a metallic bond. You're changing an intermolecular force. So it would be like holding hands and you just aren't holding hands anymore, right? It's not like we're ripping your arm off. That's terrible. So if you're talking about something that's intra means within, okay? So that's where you're talking about bond types. Now, intermolecular forces, that's how these little guys can climb up the walls of a little aquarium. I actually took this picture at a museum a couple of years ago when I was visiting my parents. But that's how, these little reptiles can climb up the walls. It's due to intermolecular forces that form between the little toesies, the little beans, and the walls of their aquarium. In terms of strength of forces, it's based really on energy here. So, a covalent, an actual bond is going to be stronger than any of the intermolecular forces that we're going to talk about. But hydrogen bonding is pretty strong, but you could see the difference in magnitude here. How much energy it would take to break one of these connective forces. Covalent bonds for about on average 400 kilocalories per mole, whereas hydrogen bonding is only 12 to 16 kilocalories per mole to break those. So an intermolecular force is an attraction between molecules. It's not nearly as strong as the bond that holds that molecule intact. It's a temporary force. So this would be like you, and this would be with a really long arm, and this would be your friend also with a very long arm, and that would be you holding hands. So the forces that hold you within yourself are strong, right? It's difficult to rip your arm off. And the force that holds your hand to your friend's hand is weak, but you're not allowed to touch each other right now because of social distancing. These forces, though, are strong enough to control physical properties like boiling and melting points, vapor pressures, and viscosities. Okay, so this is really where you'll get question parts for AP questions. Explain in terms of the type of intermolecular forces present, why substance X has a higher boiling point than substance Y. Okay, so all intermolecular forces as a group, hydrogen bonding, dipole attraction, London dispersion forces, they're referred to as van der Waals forces. Okay, a van der Waals force is not a particular type of intermolecular force, it just encompasses all of them. So in my opinion, you should just delete that term from your memory and just refer to intermolecular forces as intermolecular forces. You can abbreviate them IMFs, everybody will understand what you're talking about. So the different types of intermolecular forces, London dispersion, ion dipole, dipole, and hydrogen bonding. So we're going to go through all these different types. Starting with London dispersion forces, so I'm actually going to cover these from weakest to strongest. The other video I'm asking you to watch on Edpuzzle that another teacher presented is also covering them in this order. So London dispersion force is named after a dude named Fritz London. Pretty cool. These are forces of attraction that are present in all molecules. So if you are ever asked, identify any type of intermolecular force that exists for this particular substance, you always want to write London dispersion forces. You can abbreviate that LDF, everybody will know what you're talking about. Okay? So all molecules experience London dispersion forces. If you are a nonpolar molecule, a symmetrical molecule, that is your only type of intermolecular force. There are different factors that would influence the strength of London dispersion forces. It's not like a blanket strength or weakness to them. So London forces, dispersion forces, LDFs, any of those things are interchangeable. So the way that these work is that it's because of a temporary shift in electrons that causes an instant dipole to occur. So when you have a nonpolar molecule, a symmetrical molecule, keep it real simple here, right? Symmetry. We have an equal distribution of charge. Those two elements are sharing their electrons equally. It's symmetrical in shape. So that electron cloud is going to be symmetrical in shape. Okay, the electrons evenly circulate the molecule. So what happens if I have a hydrogen molecule next door to another hydrogen molecule? So both of these have the same exact type of bond, same type of shape, they're both symmetrical. They're just going to be bouncing off of each other, right? Hydrogen is a gas at room temperature because its force of attraction is very weak, right? This here is like nothing. But if you have a random motion of electrons, let's just say these electrons, now they're going to avoid each other, right? Because they're all negatively charged, but let's just say those electrons temporarily just shift to one side of that nonpolar molecule. Well, now what you end up with is a instant and temporary partial negative side to the molecule and partial positive side to the molecule. What it does is this first molecule induces its neighbor to do the same thing. So the partial positive end of that molecule will attract the electrons from its neighbor molecule towards this side, right? Because opposites attract. So it causes the neighbor to be temporarily and instantly a polar situation. And what can happen there is those two molecules can temporarily attract to one another. That would be the London dispersion force. Now, obviously, since electrons are constantly in motion, this is really weak, it's really temporary, because as soon as those molecules shift, they break apart. Now, other real-life examples of this, like dry ice. Dry ice is solid carbon dioxide. Carbon dioxide is a gas at room temperature. Why? Because it is a nonpolar molecule with really weak intermolecular forces, right? It's symmetrical. If I cool it down enough, though, those molecules come closer together. An instant dipole on one of those molecules can induce and cause like a chain reaction of inducing, right? Induce means, right? It makes something happen. It makes the other ones next door kind of become polar as well. This is just a diagram of how it works as well. So you have, this would be like in a noble gas. If I had a noble gas, right, noble gas are gases, but you could cause those noble gas atoms to attract to one another. If atom A has an instant dipole, it can induce a dipole on atom B, causing them to temporarily attract to one another. Okay, so thinking of your noble gases, helium, neon, argon, krypton, radon, xenon. I think I got them all in order. Maybe it's xenon, radon. My bad. Now, it's more likely and it's stronger in radon and xenon than it would be in helium and neon. And we'll talk about factors that would affect the strength of the LDFs. This is just the example that I drew out on the previous slide. This is the same thing I was just saying. Helium, let's say the electrons shift to the side, and then it gives a temporary polarity to that atom, and the one that comes next door to it, the electrons would draw towards it. It's the same thing. You can read this yourself. There's a lot of slides here. Okay, this vocabulary word, this is something that I'm asking you to define on the notes sheet when you watch the second video. Polarizability. This is an awesome word. This is like how Coulombic attraction was our word du jour for atomic structure. The polarizability is what we want to look at when we're talking about intermolecular forces. So different molecules have different tendencies to become polar. So the ability or tendency for a molecule to become polar due to its shifting of electrons is called the polarizability of the molecule. They like salivate over it. So it's a good word to use. Like if you have to justify why, if I have two non-polar molecules, why is this one's boiling point so much higher than the other? Oh, because its electron cloud is more highly polarizable. Give me a point, reader. So here are factors that will affect the strength of dispersion forces. The molecular shape will affect it, okay? A long molecule will have a stronger intermolecular forces than a shorter molecule. So if I had pentane is C5H12. If you were drawing a structural formula for pentane, N-pentane, it would look like this. So it would be hydrogens attached to all those places. I don't feel like drawing them, okay? Another version of pentane would be this. Okay, these are isomers. Okay, we don't do organic at all, but isomer is something that you should know the definition of. So isomers have the same exact formula, molecular formula, but they have different structural formulas. So both of these molecules are nonpolar. Okay, they're both symmetrical. So the only intermolecular force at play for both of these molecules are London dispersion forces. Now, the boiling point of N-pentane just means it's in a straight line, is 309.4 Kelvin, whereas neopentane, which we would probably call it 2,2-dimethylpropane, yeah, organic, its boiling point is lower. It vaporizes more easily. Well, if something vaporizes more easily, it means it has weaker intermolecular forces. So the reason why is because of how the molecules can orient themselves in relation to one another. So these first two pentanes in that straight line, they can basically just rest on top of each other and form dispersion forces in multiple locations along that molecule. It would be like stacking a plank of wood and another plank of wood. It's pretty easy to stack because there's many points of contact. Whereas if I'm looking at these second molecules that are more, they're more compact in shape, they're not that linear shape, when they come in contact with each other, there's not as many physical places where they're able to touch and form an attractive force. It would be like trying to put a basketball on top of another basketball, right? Fewer points of contact, more difficult to do. Okay, so more of the surface area in that longer molecule means a stronger dispersion force. You could also argue that, the longer the molecule is in general, the stronger the intermolecular forces would be, and I think that's addressed in a slide coming up. Okay, well this it's not, but this is a different factor. Another factor that will influence the strength of intermolecular forces is the molecular weight, and you don't ever want to justify an answer by saying it has a higher molecular mass. You want to say the molecule is larger, it has a larger electron cloud, which means greater polarizability. So that's kind of like your chain reaction thought process when you're trying to justify difference of strength of intermolecular forces based on size. So here, the ones I just highlighted in green, those are your halogens, right? Looking at the weights of these halogens and comparing them to their boiling points. Fluorine and chlorine are gases at room temperature, right? Room temperature would be about 298 Kelvin, right? Those two vaporized before that. Bromine's going to probably be a liquid at room temperature. Right, it's one of the only liquids on the periodic table, including mercury, right? Iodine is a solid at room temperature. Why? Because the intermolecular forces between iodine molecules is stronger due to the larger electron cloud and more polarizability of the molecule. If there's more electrons moving, that means there's more electrons that have the ability to shift to one side of that molecule and induce a stronger dipole on the neighbor. The same rule would apply here for your noble gases, right? The boiling point of helium is close to absolute zero versus xenon, which has a much higher boiling point. These are obviously all gases at room temperature, but why is xenon's boiling point so much higher than helium's? Larger atoms, larger electron cloud, more highly polarizable. Oh, this is what I was talking about with the hydrocarbons, like methane. Here, this one's methane, ethane, propane, butane, pentane, octane. Okay, so if I took all of these molecules and sketched out their structures, okay, you can see the pattern here. There's 4, 5, and then 8. So all of these are polar in shape. All of these are non-polar in shape. They're all symmetrical molecules. So the only intermolecular force at play would be dispersion forces. There's 8 there, yeah. Now, why is it that the boiling point of octane is so much higher than the boiling point of these other molecules? Larger molecule, larger electron cloud, because the electrons they're delocalized, they're on the whole surface of this molecule. Larger electron cloud, more highly polarizable. You could also address that the octane has a greater surface area that allows for more points of contact with a neighboring octane molecule as compared to the others. Okay, but if you're just looking to compare them based on weight, larger electron cloud, even though the electrons aren't factoring into the mass much at all, right? Because electrons are so tiny, for every proton you're adding another electron. So the more protons you have in all those atoms collectively, the more electrons you're going to have in your molecule. The next type of intermolecular force that we're going to look at would be a dipole attraction. So a dipole force is when you have polar molecules. Okay? So these are kind of the next in terms of strength. They're stronger than dispersion forces. They're not as strong as actual bonds. So this type of interaction really isn't technically an intermolecular force because you're talking about a molecule and an ion here. But this is when you're looking at solubility, right? How a molecule can dissolve in something like how an ionic compound can dissolve into something like water when you're talking about the dissociation of the ions. So if you had to draw an interaction, I know this comes up on like Regents questions, But if you said, okay, well, here's my calcium ion, let's show how water molecules would attract to it. Well, there's my water molecules. The oxygen end of the water molecule is the negative end because of its greater electronegativity value. That would be the ion dipole interaction. This is actually an animation in my PowerPoint, but this what it shows is the water molecules coming over and basically tearing apart the ions. So the attraction of the positive end, the hydrogen end of the water molecule would pull on the negative ions in the ionic crystal, and the negative part of the water molecule, which is oxygen, would attract to the positive ions. Dipole moment, this I mentioned in bonding chapter. This is when you have a polar molecule, an actual polar asymmetrical molecule. You would use an arrow to represent the dipole moment. The arrow would point towards the negative end of the molecule, and the tail of the arrow would be left behind towards the positive area of the molecule. The way you determine that is based on electronegativity values, and again, you don't have to memorize electronegativity values, but just understand the trends, right? Oxygen is further to the right, it has a higher electronegativity than hydrogen would. If you have a molecule like carbon dioxide, so these bonds, these are double bonds, they don't have it there, but these bonds are both polar covalent, right? They're unequal sharing of electrons between the carbon and the oxygen. But because if I draw that polarity of the bonds in the form of an arrow, they're symmetrical to one another, they cancel each other out. That molecule itself would be nonpolar. So if you had to justify the polarity of or a non-polarity of a molecule, you would say symmetrical distribution of charge, or no net dipole would be fine. Now, if you have actual permanent, real polar molecules, so we're not talking about inducing or temporary situations, but if I have actual asymmetrical molecules, they will orient themselves such that the positive end of one molecule would interact with the negative end of a neighbor. So in this diagram, the solid red lines would be attractive forces between oppositely charged ends of molecules, and the blue dotted lines would be repulsive forces between those ends of the molecule. So they're going to orient themselves so that opposites attract. Basically, if you took a box of magnets and shook them together. The more polar the molecule, the higher its boiling point is. This is data. Obviously, you don't have to memorize boiling points or anything. But if you were given like these formulas and given this boiling point data, and you were asked to explain, like looking at like molecular weights are all pretty similar here, right? So you can't say, oh yeah, it's the heavier one must have the strongest type of intermolecular force. Well, no, that's not true at all. So you would have to say that the acetonitrile is just a more polar molecule, and it would have stronger dipole attractions. So this graph shows boiling points of covalent hydrides. Okay, so what you can see here is some trends. The blue follows a really nice trend. So carbon, silicon, germanium, and tin are all in group 14. 4A is group 14, same thing, 15, 16, 17. Okay, so those are all group 14 elements, and you can see that the compounds that are made up of those elements with 4 hydrogens attached, right, because they all have 4 valence electrons, similar chemical properties, similar bonding, those all be tetrahedrons. You can see they follow a nice trend. Now, what you would also notice here, looking at the red, the red, the green, and the yellow lines, is you don't have that nice, low value for the first member of the series and then a continuous increasing. It doesn't follow that predictable trend. And there's a reason for that. The explanation for this would be because it's a different type of intermolecular force that exists in the water, in the hydrogen fluoride, and in the ammonia than what exists for these others. And that is, ta-da, hydrogen bonding. So hydrogen bonding is your strongest intermolecular force. Okay? So it's a type of dipole interaction. So we're going to have a polar molecule again. You're going to have an asymmetrical molecule. But there's a special circumstance that exists for hydrogen bonding to take place. The molecule that you're looking at must have hydrogen in it. The hydrogen needs to be bonded directly to either nitrogen or oxygen or fluorine. Sometimes they throw chlorine into this mix, but for AP, I wouldn't bank on it. I would just go with those three. Hydrogen with fluorine, hydrogen with oxygen, hydrogen with nitrogen. When you have those types of molecules, because nitrogen, oxygen, fluorine are highly electronegative, those elements pull electrons towards them. They shift the electron density in that molecule and make it very asymmetrical in terms of the distribution of charge. So here's your hydrogen bonded directly to oxygen, hydrogen bonded directly to oxygen. So when a water molecule attaches to another water molecule, that is called a hydrogen bond. I hate the fact that it's called a hydrogen bond because it's not a bond. It's an intermolecular force. If you wanted to call it a hydrogen FOA, force of attraction, that's fine, but you'd probably just see it as hydrogen bonding. With the ammonia molecule, nitrogen or hydrogen is bonded directly to nitrogen. Hydrogen is bonded directly to nitrogen. So in this molecule, this is the same for all of these, but the nitrogen is pulling those electrons towards it. So there's a lot of electron density here. So this is really partially negative. This is really partially negative. So that kind of leaves this hydrogen exposed, like a naked proton, right? Because the electron that's involved in this bond is very rarely near the hydrogen. It's really concentrated towards the nitrogen. It's like my children draped all over me, even though their dad's sitting right across the room. Okay? So this takes on a really partial positive charge, which makes this hydrogen bond a pretty strong force of attraction. The same thing would happen if you had an ammonia molecule and a water molecule. That would be a hydrogen bond. Hydrogen fluoride is another one. Fluorine is the most electronegative element that there is. So there's a very strong polarity here in the direction of the fluorine, leaving that kind of naked proton here. So partial positive, partial negative. So when another hydrogen fluoride molecule comes along, they can form that intermolecular force there. I just really explained this. It's a strong dipole force. Those are very highly electronegative elements. They form very polar bonds when they bond with hydrogen. Those are your big three that I would remember. Alcohols are like this as well. So if I have ethanol is drinking alcohol. So right here, I have hydrogen bonded directly to oxygen. So if I had another ethanol molecule nearby, I would have the intermolecular force, that hydrogen bond would be between those two. And this region here would not be in a straight line. Let's think about the oxygen here. This oxygen has 4 electron domains. So it has tetrahedral electron geometry. But 2 of those are lone pairs. 2 lone pairs, 2 bonds. So the shape around this oxygen would be bent. It would be angular, like it is here. So it would really be like this. So you can see how there's like a region where that neighboring, this is all janky right now, but you can see there's a region where that attraction could really pop in, and that would hold the molecules together. This happens in DNA and RNA. So if you remember from biology, like with DNA, the double helix, the A, the T, the C, the G, when you form that ladder structure, you have your deoxyribose and your phosphate groups forming that size to your ladder, and then you have these nitrogenous bases, the adenine, thymine, cytosine, guanine. They attach to one another through hydrogen bonding. Now, why is it? Now, if you took AP Bio, you may remember this. Now, why is it that adenine can only bond with thymine? It's not really bonding as intermolecular force. Or why is it that cytosine can only attach to guanine? It's because of the shape of the adenine, what's it called? Nitrogenous base, and the shape of the thymine both allow for, it's either 2 or 3. I know that like adenine and thymine might each have 3 sites for hydrogen bonding, whereas cytosine and guanine only have 2 sites. But I can't remember if it's that way or the other. But anyways, the shape of the molecule only allows for a certain place for the interactions to take place, versus, this one might have 3 locations for the interactions to take place. It's the same idea with enzymes. Like, why are enzymes specific to substrates? It's because of the intermolecular forces that can form between the enzyme and the substrate. The shape of the molecule dictates its interactions with other molecules. It's very important. Looking at like channels in the cell membrane, all about physiology here. Okay, this is the same thing again. Hydrogen bonding arises in part from the high electronegativity of nitrogen, oxygen, fluorine. When hydrogen's bonded to one of those elements, a hydrogen nucleus is exposed on the other side. That's that naked proton. There's no lone pairs around there. There's your water molecules stuck together, right? Here's a water molecule. Here's a neighboring water molecule. Here's another neighboring water molecule. Those would be hydrogen bonds. Oh, look, it's another one showing you. Between ammonia and water, just more examples for you. Oh, here's your DNA. Look, it was 2 for the A's and the T's. Aww. So this is this is a phosphate group. This would be the deoxyribose. And this would be the nitrogenous base. Look, nitrogenous base. All the other vertices here would be carbons. You'll learn this if you take organic, also, thoughts and prayers. But it's because of the different places that they're able to interact. That's what dictates the base pairing rules. And there's your C's and the G's with 3 spaces. Look at that. I thought I had this in here. I couldn't remember. This just shows you that graph again with boiling points. So it should make more sense now that those molecules have higher boiling points than their counterparts that fall within the same group, like oxygen, sulfur, selenium, tellurium are all in group 16. But why does the water molecule have such a much higher intermolecular force, even though it's such a small molecule, right? Molecular weight-wise, its London dispersion forces are probably a lot weaker. But the fact that it's able to do hydrogen bonding is what jacks that boiling point way up. So same thing here. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. Hydrogen iodide has the largest molecular weight, so it would have the strongest LDF, because every molecule, even though this is an asymmetrical molecule, right? It's polar, but every molecule has London dispersion forces. So this would have the strongest dispersion forces. This would have the weakest dispersion forces. But the fact that this can do hydrogen bonding with its neighboring HF molecule, that trumps it. This chart is also posted in OneNote as a separate page. I think it's called like IMF summary chart or something like that. But this is a really nice way to remember it. Which molecule is capable of forming stronger intermolecular forces? Okay, so let's talk about what these molecules look like. There's your nitrogen molecule. Here's your water molecule. So now you would have to label the types of intermolecular forces. LDF, LDF, because everybody has LDF. But water molecules also have hydrogen bonding. Okay? So this would be the stronger intermolecular forces because of the fact that it could do hydrogen bonding. So that's your summary for intermolecular forces. The next video is another teacher's presentation of this. That's what I want you to watch while you fill in your answers to the notes 1 of 4 worksheet, and then complete the rest of the assignments on that sheet. Bye.